And the final part of parametric equations is going to be parametric integration. So what we've got here is just like with normal definite integration, is we've got a curve, y is a function of x, and we want to find this area here that's shaded. The problem is we don't have y as a function of x, we have y as a function of t, and x is a function of t, where t is a parameter. So we can't just find the integral of y between a and b with respect to x. It's a bit more complicated than that, but let's start with that, because we know that that is true from our year 12 knowledge of areas. Okay, so we know that the area is equal to the integral from a to b of y with respect to x. The problem is y is not a function of x. So it's actually going to be the integral of g of t, which is a function of t, with respect to x. So that's an issue. Just like with differentiation, we couldn't differentiate a function with one variable with respect to a different variable. The same is true for integration. We can't carry that out as it currently stands. So what I'm going to do is, just like with integration by substitution, I'm going to replace the dx with some kind of dt. And the way I'm going to do that is I'm going to consider my definition of x in terms of t. So I can take x in terms of t and I can differentiate. So I get dx by dt equals f primed of t. Okay, that's just taking this definition and differentiating with respect to t. And this tells us then that dx is equal to f primed of x, f primed of t dt. And I've put little quotes around it because this is not a fraction, and I've just treated it exactly like a fraction. Dx by itself doesn't really mean anything. However, mathematically, this does work out, even if this line itself is not mathematically sound. So what I can do is I can replace the dx with f primed t dt. Okay, so let's have a look at what that looks like. So this tells us that the area is now going to be the integral from, I'm just going to emphasize that it's x equals a to b, of g of t times dx, but dx is f primed of t dt. Okay, so we're making progress. We've now got a function of t being integrated with respect to t. So that's good. The only issue left now is we have our limits are still in the x world, so we need to somehow convert them into t limits. You can't integrate a function with respect to t and then plug in x variables or x limits. So what we're going to do is we're going to convert these to t limits. So you use the definition up here. We've got x is a and b, and we want to find this value here. So you'd need to algebraically solve this equation for some particular value of x. So let's just call it for now f inverse of a and f inverse of b. Although it might not be as simple as that. Because, for example, you might have the curve coming back on itself. So you have multiple t values for one x value. So you've got to be careful and make sure you choose the right t value. So in terms of notation, I think that'll be fine. We can just call it t1 and t2, where t1 is the point at the initial and t2 is the value of the parameter at the end. That might be a better way to put it. So we end up then with the area as being equal to the integral from t1 to t2 of g of t times f primed of t dt. Okay, so that's essentially what we're going to be doing. It is really just a fancy integration by substitution with a complicated substitution. Okay, but that's the process that we're going to carry out. So I've got two example questions which I want to have a look at. So to show you, the first one's quite a simple one, and the second one's a bit of a trickier one. Okay, so here's my first one. We're going to calculate the area of the shaded region, and we can see that it goes from x is 0 to x is 3, and x is 3t squared, and y is e to the t minus 1, and we're told that t goes between 0 and 1. Okay, so let's start with our year 12 knowledge. We know that the area, the shaded region here in orange, is going to be equal to the integral from 0 to 3 of y with respect to x. Now that's going to be equal to the integral from 0 to 3 of e to the t minus 1 dx. Okay, so we need to change the dx into a dt, and we also need to change these x limits to t limits. So let's consider this definition. Dx by dt is going to be 6t. Nice, straightforward derivative there. So that tells us that dx is going to equal 6t dt. And I'll put this in quotes, but if you don't put it in quotes, you won't lose any marks. So that solves that problem. And now we need to solve this problem over here. The x limits need to change to t limits. So x equals 0. We're solving the equation 0 equals 3t squared. That only has the solution t is 0. And x equals 3. Okay, x equals 3. So if we solve this quadratic, we end up with t is equal to either plus or minus 1. But interestingly, there's only one point on the curve where x is 3. Well, let's just have a look at the domain here. We're told that t is between 0 and 1. So actually, t is minus 1 is not on the curve at all. So we only want t to be 1. So when x is 3, t is 1. And when x is 0, t is 0. So these are the limits we're going to use. Okay, t is 0 to t is 1. And make sure you get them the right way around. Sometimes this might be less than this number. So you need to make sure that the 0 replaces the 0 and the 1 replaces the 3. Okay. So the area now is going to be equal to the integral from 0 to 1, because we're now in the t world, of y, which is e to the t minus 1, times dx, but dx is 6t dt. Okay, perfect. Now we don't have to go back to the x world at all. This integral will give us our area exactly. So to integrate this, we're going to need to use integration by parts. So u is going to be 6t. Okay, if you follow the late rule, check out my previous video for what I'm doing here. U primed is 6. V primed then is e to the t minus 1. And v is also e to the t minus 1. And we're going to use these definitions in our integration by parts formula. So the area is going to be equal to uv, so that's 6t times e to the t minus 1, between 0 and 1, minus the integral between 0 and 1 of vu primed, so that's 6e to the t minus 1 dt. Okay. And the reason I've done that is because I've now taken this integral, which is not standard, and transformed it into this one, which is now a standard integral, so I can just state the answer. So it's going to be 6t times e to the t minus 1 minus 6e to the t minus 1 between 0 and 1. Perfect. Okay, now we plug in our limits. So these are t limits, so that's fine. I can just put them straight in. So I get 6 times e to the 0, which is 1. So it's just 6 times 1 times 1 minus 6 times 1. Plug in 0. 6 times 0, 0, doesn't matter what this is. And then minus 6e to the minus 1. So the answer then is just 6e to the minus 1, or 6 over e. And that's the answer. That is the exact area of that orange bit there. Okay, 6 over e. If the question asks for the exact area, you must leave it in terms of e. If it asks for the answer to 3 significant figures, then we can approximate that. I get the calculator out. 6 divided by e is about 2.207. 2.207. If it asks for it to 3 sig fig, you must leave it to 2.21 or 3 decimal places, 2.207. If it doesn't specify an accuracy or an exact, then it doesn't matter. Just leave it at 3 significant figures or better. Personally, I would leave it as 6 over e in that situation. Okay, right, that was example number 1. That was the simpler of my 2 examples. This one is a bit more complicated. Okay. So what I've got here is I've got a parametric definition of a curve. That is the whole curve. It does stop here and here. But I'm only interested in when x is positive. So this kind of bubble bit that's sticking out from the y-axis here. And I want to find the area of that exactly. So I want the exact area of this. The definition of this, this curve is given parametrically as x equals 2 pi t minus t squared and y equals sine t plus 2. and we're told that t takes values between minus pi on 2 and 5 pi on 2. Okay, calculate the area of the shaded region, giving you an answer exactly. So think back to year 12, when you're trying to find the area between two curves. What we're going to do is we're going to integrate from here to here, the top curve. That'll give us this big area here. And then we're going to subtract the area underneath the lower curve between the same values here and here. And that'll give us this area that's left in between. So it's exactly the same principle, it's just that in this case, the top curve and the bottom curve are the same curve, they're just defined for different values of t. So under here I just illustrated exactly what I'm going to be attempting to do. The area of the region I'm trying to find is going to be equal to the area under the top curve, subtract the area under the bottom curve. Okay, so I'm going to find two integrals, which the first one will give me this area, second will give me this area, and the difference between them will be the area I want. Okay, so that's the principle I'm going to execute here. Okay, so I guess the first thing to do is to decide what is the value of t here. Now I don't actually know the value of x here, and actually I don't overly care either. I could find it. I could find it by finding dx by dt and maximising x as t varies, but I don't need it. I only need the value of t at that point. So what I'm going to do is I'm going to state what the area is going to be, and I'm going to call this T1, I'm going to call this T2, and then I'm going to call this T3. Okay, now T1 and T3 are the same point, but they're different t values. Okay, so the same point in the xy space, but they are different t values, and that's important because we're at different points on the curve. Okay, one is coming up this way and one is going up this way. So just be careful when you've got two t values of the same point. This can happen with parametric definitions. Okay. So the area that I want is going to be equal to the integral from the top curve, which is t equals t1 up to t2 of y with respect to x. And I've emphasised that it is t equals t1 rather than x equals 0. I've already kind of changed the limits, if you like, minus the integral from t equals t3 to t2. And this is also important. It's tempting to do t2 to t3, but the problem is that's going backwards in the x direction. If you follow the values here, as t increases, then you'll follow t is this one here. T is minus pi on 2, and this point here, t is 5 pi on 2. So as you follow the curve round, the t values increase, meaning you're going this way. Okay, so that's the kind of direction of the curve as t increases, and that's important because the area under this curve here is going from x is 0 to x is capital X along the bottom curve, which is t3 to t2, even though t3 is bigger than t2. So you can get integrals where the bottom number is bigger than the top. Okay, and this is such a case. No, that's because the curve is going backwards. It's going from right to left. Okay, of y with respect to x. Okay. Right, we've got y in terms of t, so that's nice and straightforward. We can find dx in terms of dt by just differentiating that, so that's also fairly straightforward. The only issues that we have is actually finding the values of t1 and t2 and t3. Okay, so what I'm going to do is I'm going to set x to be 0, because that will give us the values of t1 and t3. Okay, and t1 is going to be less than t3 because of what I said, it's increasing as we're going around, and t1 is actually going up, and then t3 is actually coming back. Okay, so t1 is less than t3. Maybe I should emphasise that down here. It's t3. Okay, so at this point, x is 0. So x equals 0. That tells us that either t is 0, because we're solving this quadratic. Okay, x is 0. So t is 0, or t is 2 pi. Okay, and both of those fall in range. because we're going from minus pi on 2 to 5 pi on 2, so those look about right. So we're going from 0 to 2 pi altogether. We need T2 as well. Now T2 occurs when x is at its maximum. So I'm going to find x dot, which equals 2 pi minus 2t. And if I want to set that to be 0, then that tells me that t is equal to pi. Okay, so that is over here. And this is not something I've necessarily seen before in any of the videos I've done, but I'm essentially just maximizing x. Okay, the point where x is being maximized is when dx by dt is 0. Okay, you can kind of view it as x as a function of t. In the xt world, what value of t maximizes x? Okay, and we get t as pi. Okay. Another way to consider it is x is a quadratic in t, and we've already got two roots at 0 and 2 pi. So by the symmetry of a parabola, the turning point must be halfway, so pi. Okay, so that's another way to consider it. But either way, we end up with t1 is equal to 0, t2 is equal to pi, and t3 is equal to 2 pi. Okay. The only thing left to do now is to find dx as a function of dt. So back to the definition up here. I'm going to find, oh, if you know what, I've already done it over here. That is dx by dt. So that's going to be dx is equal to 2 pi minus 2t dt. Okay. So differentiating actually gave us two purposes. Okay, so I've now got everything I need to carry out my integral, or find my integral, sorry. So the area is going to be the integral from t equals t1, which was 0, to t2, which is pi, of y, which is sine t plus 2. And that is times by dx, which is 2 pi minus 2t dt. So that's the first integral. Subtract the second integral. So I'm going to subtract the integral from t3 was 2 pi, to t2, which is pi, and there we go, that feels wrong, but it is right, of the same thing, so sine of t plus 2 into 2 pi minus 2t dt. Okay, so the area is going to be given by this integral, or these two integrals. So I'm going to carry both integrals out, and then right at the end of the video, I'm going to show a slightly quicker way that works in this case. But I wanted to execute both integrals because you can't always simplify the way I can with this one. Okay, so if you spotted something between these two integrals, just hang fire. I will come back to that a bit later. Okay, so the first things first then is I actually need to find out what function differentiates to the contents of the integral. Okay, and I'm going to do that by carrying out the integral. So it's going to be 2 pi times sine of t plus 4 pi minus 40 minus 2t times sine of t dt. And I'm just going to carry this one out as an indefinite integral, and then I'll plug in my limits. This integrand is the same for both integrals, so once I've got the answer, it's good to go. Okay, sine integrates to, I'll check my answers here as I go. Okay, so sine integrates to minus cosine, so it's minus 2 pi times the cosine of t. 4 pi integrates to 4 pi t. Minus 4t integrates to 2t squared. And for this, I need to do an integration by parts because I've got a t times a sine t. So I'm going to say u equals, let's go with minus 2t. U primed then is minus 2. V primed is sine of t. And then integrate that to get v, which is minus cosine of t. Okay. So that's going to give me plus uv, which is 2t times cos t, minus the integral of VU primed, and that's minus, minus, and minus, so it's minus altogether. It's 3 negatives, 2 cos t dt. And now I can integrate that. So I get minus 2 pi times the cosine of t plus 4 pi t minus 2t squared plus 2t times cosine of t. And then cos integrates to sine. So I get minus 2 sine of t. Okay, and then the plus c, but I don't need that. Okay, so that is my integrand. So that's what I'm going to be plugging my limits into. So let's just turn the page and copy that one over. So my area then is going to be equal to 2 pi times, sorry, minus 2 pi times the cosine of t plus 4 pi t minus 2t squared minus 2t, plus 2t times the cosine of t minus 2 times sine of t. And that is evaluated, my first integral, between 0 and pi. And then you subtract the same result, 2 pi times the cosine of t plus 4 pi t minus 2t squared plus 2t times the cosine of t minus 2 times the sine of t. And that was evaluated between 2 pi and pi. Okay, so that's what I'm evaluating. So let's plug in our limits. Pi into here, cos of pi is minus 1, so that is positive 2 pi. Plug in pi into here, I get 4 pi squared. Plug pi into there, I get minus 2 pi squared. Cos of pi is minus 1 still, so that's minus 2 pi. And then sine of pi is 0, so it disappears. Plug in 0, cos of 0 is 1, so that is minus minus, that's plus 2 pi. Minus 0, minus 0, minus 0, plus 0, so everything else disappears. So that's the first bracket. Minus the second bracket, plug in pi, so that's cos of pi, so that is minus 1. Minus 1 times minus 2 pi is plus 2 pi. Plus 4 pi squared. Minus 2 pi squared. Plug in pi, that's minus 1, so that's minus 2 pi. And then sine of pi is 0. And now plug in 2 pi, cos of 2 pi is 1, so that's going to be minus 2 pi, but I'm subtracting that, so plus 2 pi. Plug in 2 pi there, I get plus 8 pi squared, which is minus 8 pi squared. And then I've got plus 8 pi squared. Plug in 2 pi into here, that's cos of 2 pi, which is 1, so that's 4 pi, so I'm subtracting 4 pi. And then again, 2 pi into there, disappears. A lot to plug in there. Everything's got either a pi or a 2 pi, which is, a pi or a pi squared, so I can cancel some things. So that cancels with that, that cancels with that, that cancels with that. 2 pi minus 2 pi, they cancel out. Here I've got 2 pi squared, here I've got 2 pi squared, but I'm minusing it, so actually those cancel out. So I'm only left with 4 pi. And that's the answer, 4 pi. The area between those two curves is exactly 4 pi. Okay, I did promise a quicker way to do this integral here. All I'm going to do, just to show you what I could have done, just to make my life a little bit easier, is I can combine these two integrals by swapping these two limits. So that now becomes a pi, and that becomes a 2 pi, and then changing the sign. Okay, so I'm taking advantage of the relationship, the integral from a to b of something with respect to something is exactly the same as negative the integral from b to a of something with respect to something. So if you swap the limits and times by -1, you can you can change the limits around. And the reason why I've done that is because now I'm integrating from 0 to pi, and I'm adding the same integrand from pi to 2 pi. So I can actually combine these two integrals in this case to be the integral from 0 to 2 pi of sine of t plus 2 times 2 pi minus 2t dt. So I could have cut my work almost in half during my substitution process. And if you evaluate that, you do get the answer 4 pi as well. So you could have done that if you'd spotted that. Okay, so the area is exactly 4 pi. And thank you for watching.